So I think we're doing pretty good in our venture into the wonderful land of full quantization in binary mechanics. And our character hasn't had to use any health packs or stim packs because we haven't taken any damage. And so let's proceed. We've reversed engineered the secondary constants below and to obtain primary constants above. And then with those primary constants, we can calculate the unexplained observed values. Let's look at this quest in a little bit of detail. A series of papers document this second quest. We can do a quick walkthrough of the papers published in the Journal of Binary Mechanics, which establish that we can calculate from the primary constants of binary mechanics the measured observed values of the so-called fundamental constants, which I call secondary constants. First, we have zero electron electric dipole moment. Here is the electron quanta cycle, where the two types of energy, quanta, shown by circles and arrows, revolve around a central axis shown by the gray dot here, which is perpendicular to the page. There is no collection of charge on one side or the other, and so the what we call the electron electric dipole moment is zero. And this agrees with findings of major labs, which have thought that the shape of the electron therefore must be like a sphere. But in fact, in binary mechanics, it's more like a spinning top shape. Unlike the electron, the proton has a non-zero electric dipole moment. It's sort of like a water molecule where one side of the water molecule is more positively charged than the other side. That's what we mean by an electric dipole moment. This finding also agrees with experimental results from major labs. The electric charge positions can be viewed in sort of an X-ray fashion where the dark red is plus and the yellow is minus charge. And you can see from these two views that the plus charge is more to one side of the proton and the negative charge is to the other side. Here is a detailed analysis of the positions of quanta in the proton bit cycle, which was used in this analysis. Next, we have the fine structure constant derivation, where the fine structure constant was plotted versus quanta density, shown here. Alpha is simply the ratio of the scalar and vector bit operations, which involve electric for scalar and magnetic for vector, divided by the number of M-type quanta available to be accelerated by these two potentials, scalar and vector. That is the definition, very simple, in binary mechanics of the alpha coupling constant. Running the binary mechanics lab simulator, we find that the fine structure constant alpha varies somewhat when plotted against quanta density. The red arrow shows the accepted value of about 0.00729. Intrinsic proton spin derivation. This is one of several papers that derived the measured value of Planck's constant h from analysis of quanta spinning in the proton bit cycle. Here is the proton bit cycle showing that it contains 42 locations and that quanta move around this circular area here in the proton bit cycle and have an intrinsic angular momentum. Light speed derivation. We can fire one state quanta into a simulation using the binary mechanics lab simulator and measure the speed of light by noting the arrival time of these quanta to the other side of the simulation. If we have a cubic volume that we're simulating and we shoot quanta in for a light signal on one side, we can see how many ticks of the binary mechanics lab simulator are required before these quanta arrive at the other side. That's what this unidirectional light speed measurement data is showing. Here are the details of how all of that was calculated. The calculated light speed, of course, is bit velocity v divided by pi, so that we can express light velocity in bit velocity units of 1 over pi. In those units, light front velocity was approximately 0.319, or within about 0.3% of 1 divided by pi in bit velocity units. This is a remarkable result. Elementary charge derivation. We can take a look at what happens with the electrostatic force in the scalar bit operation. If two like-signed charge, these are the M-type quanta shown by circles, if one moves this distance, the separation then is the hypotenuse, and we can calculate what the electrostatic force actually is, and therefore determine, using Coulomb's equation, what the value of the elementary electric charge is. Intrinsic electron magnetic moment derivation. Our calculations give you the measured value in joules divided by Tesla units for the Bohr magneton. So finally, unexplained measurements are now all accounted for. We've done a great job. We have beat the big boss in the game of deriving primary and secondary constants. The basic result is that the primary constants of binary mechanics, shown in the green full quantization area here of our open world, have won the game of physics. Have a great day, you all.